Let's go over the 2019 version 1, paper 1. Okay, so the first one is a percent error, or rather an error propagation problem. They give us that the fractional uncertainty is 5% for period, and they want to know the fractional uncertainty for omega given this equation. Well, 2 and pi have no uncertainty at all. They're just numbers. So the fractional uncertainty in omega is just a fractional uncertainty in t because we didn't do anything to it. I mean, we divided by it, but that doesn't change the fractional uncertainties. So it's just 5%. A student models the relationship between pressure of a gas and temperature as pressure is x plus y equals t, where the units of pressure are pascals and the units of temperature are Kelvin. What are the SI units of x and y? Okay, so for this, we need to know that the units on both sides of an equal sign have to be the same. And if we add two things, they have to have the same unit. So now I know that x has to have units of pascals, because pascals is what we have on the other side. Now a pascal is, well, pressure is force per unit area. So it's newtons per meter squared, or per square meter. Now a newton is a kilogram meter per second squared. And then we've got, because of F equals ma, that's the m, that's the a. Kilograms is m, meters per second squared is the a. And then we also have our meter squared down here. So that meter will cancel out with one of those meters. We get kilograms second squares per meter. So kilogram meter in the denominator, second squared in the denominator. So that's good. That's good. These two, no. C and D are gone immediately. Now the unit for y. Now, y does need to be able to cancel out the Kelvin in the T, but it also has to give us a unit of pressure. So this is not enough. This would just have this thing having no units, a pure number. We cannot add a pure number to a number with units of pascals. We have to have units of pascals. So we have to cancel out the K, right? Temperature has units of K, so multiply it by K to the negative 1, or multiply it by 1 over K, and we cancel that out, and then we need our unit for pressure, so it's A. A skydiver is falling at terminal speed when she opens up her parachute. What are the direction of her velocity vector? Okay, so a person in a parachute, when they open their parachute, they're still going down. They just go down at a slower rate. So while the parachute is slowing them down, their acceleration is up. They don't actually move up. In movies, when they show this sort of thing, it looks like the person goes upwards. That's because the camera view they use is from the perspective of someone who did not yet open their parachute. So if two people are going down, camera, person with parachute, two people are going down at very, very fast speeds, but then this one slows down as they're going down. From this one's perspective, it will look like this one moved upwards. But they didn't. This person who opened the parachute did not move upwards. They're still moving downwards, so A and B are gone. And the acceleration, however, is upwards. Because if we're moving that way, we want to slow down, we need an acceleration that way. Okay, a stone is thrown downwards from the edge of a cliff. Let me re-say that last thing in words rather than that way and that way. If we have a velocity that's downwards, we need an acceleration that's upwards, the opposite direction, in order to slow down. You slow down when your acceleration is in the opposite direction of your velocity. Okay, a stone is thrown downwards from the edge of a cliff with a speed of 5 meters per second. It hits the ground 2 seconds later. What's the height of the cliff? All right, well, so we want delta y. We want delta y. We know time. We know acceleration. We know initial velocity. So I used equation 4. So I did negative g over 2. And instead of using 9.81, I just used 10. No calculators allowed here. Times the time, which is 2 seconds squared, minus, because you throw it downwards, minus 5. The initial velocity is negative. Now here I cross this out because I thought after I finished writing that they didn't give us the time, that we were finding the time, but that wasn't the case. So this is equation 4. So the initial y velocity is negative 5, and then the time is 2 seconds. 10 divided by 2 is 5, times 4 is 20, and then 5 times 2 is 10, so negative 20 minus 10 is negative 30. So the object went down by 30 meters, which means the cliff is 30 meters tall. Ball is thrown upward at an angle to the horizontal. Air resistance is negligible. Which of these statements is true? Acceleration of the ball changes during its flight. Nope. It's g downward the entire time. That never changes, especially if we're neglecting air resistance. The velocity of the ball changes during its flight. Yeah. As it's going up, its x velocity stays the same, but its y velocity slows down as it's going up, and its y velocity increases as it comes back down. That means, well, velocity is a vector sum of x and y. If x stays the same while y is changing, yeah, then the velocity is changing. The acceleration of the ball is 0 at the highest point. Nope. The y velocity is 0 at the highest point. The velocity of the ball is 0 at the highest point. No, at the highest point, the velocity is the x velocity. So it's B. All right, an object of mass m is sliding down a ramp at a constant speed. This is the key. You saw I started to do some work, but no, it's constant speed. That means all of the gravitational potential energy that's lost is converted into thermal energy by friction. All of the lost gravitational potential energy is work done by friction because the speed does not change. Therefore, the answer is A, mgh, which is just the reduction in the gravitational potential energy. Therefore, that is the work done by friction and the energy transferred into thermal energy. Number 7. 2 blocks of masses m and 2m. Okay. So what's the momentum before and after the collision? Well, the momentum before and after the collision have to be the same. So that immediately eliminates B and C, because that's not the same as that, and that's not the same as that. Right? They're the same magnitude, but conservation of momentum is not that the magnitude of momentum is conserved. It's that momentum is conserved, and momentum is a vector, so the direction matters. Now, what's the initial momentum? Well, they're both going the same speed, so this one has a momentum of 2m times v. This one has a momentum of m times v, but it's in the other direction, so it's negative. So the total momentum is 2mv minus mv, because this one has a negative mv momentum, which is mv. So mv. The graph shows a variation with time of the resultant net force acting on the object. So we have a force over time. And then we'll know the velocity of the object if it starts from rest and has a mass of 1 kilogram. Well, the area of a force time graph is change in momentum, or impulse. We call that impulse as well. So the change in momentum is that area. It's a triangle, therefore it's 1/2 base times height. The base is 0.2 seconds, because that's in milliseconds. Easy to miss that. Milliseconds. Look at the units on your graphs. So 0.2 times 80. Well, the 1/2 and the 2 kind of cancel out. So when I cancel this 2 out, I turn into a 1. 0.1 times 80 is 8. Now, it started from rest, so the change in momentum is equal to the final momentum, because change in momentum is P final minus P initial, and the initial was 0. So P final is the change in momentum, and momentum final then, which is equal to the change in momentum, is equal to m times V final. That means V final has to equal the final momentum divided by the mass. Just divide the mass over. That was 8 divided by 1 is 8. I think you can do that one without a calculator. We have a block on this rotating surface. What's the correct arrow to represent the direction of the frictional force acting on the block at that instant? Well, in this case, friction will be the centripetal force. Friction is the only force available to be a centripetal force. And centripetal forces always point toward the center. So it must be C. Energy is transferred into a flask at a rate of P. The water reaches boiling point, and then P is increased. So we increase the power output of our heater. What are the changes of the temperature and the water of? I'm sorry, I can't read. What are the changes to the temperature of the water and to the rate of evaporation of the water? Well, right when we get the water boiling is when we increase that. So the water is still boiling after we increase the power output. Boiling water is at 100 degrees. Right? Temperature does not increase. The temperature of the water does not increase as it boils. So the temperature remains unchanged. So A and B are gone. So now we want to know what happens to the rate of vaporization. Well, if we increase the power output we're putting in more energy per second, Well, where's that energy going when you're boiling water? It's going into breaking the liquid bonds to allow the water to evaporate as steam. Well, if we're putting more energy in, we're going to break more bonds to produce more steam each second. So the rate must increase. D. Number 11, I don't like. It assumes that all the gravitational potential energy when you turn the tube over is converted into thermal energy, which is not a good assumption. But that's what they're wanting you to do here. So we have this tube, we turn it over and heat up the little lead spheres. So they want to know the specific heat capacity of lead. Well, Q equals MCAT. We solve for C. I don't know if you can even see that C there. We solve for C, so we divide the M and the delta T over. And now the Q is the energy we put in, and that's supposed to be the energy gained, the gravitational potential energy lost from gravity each time we flip it over. And that, again, that energy is supposed to go into heat. So the energy is however many times we flipped it over times mgh. However, the mass, and you can see I kind of tried to fix it there because I wrote it wrong the first time. So each time this thing falls, it loses potential energy equal to, let me see here, N times mgl, right? Because gravitational potential energy is mgh, but m is the mass of each sphere, and we have n lead spheres, so that's the total mass is nm, and then g, of course, and then L is the height through which it falls each time, and then you do that S times. So you get that much energy S times. So then the N cancels out, the M cancels out. Oh, and the mass, of course, is the mass of each sphere times the number of spheres. So same thing here is there. So the N cancels out, the M cancels out. We're left with SGL over delta T. SGL over delta T. That's B. This is a bad question, in my opinion. I see what they're going for, but I'm not a fan of it. Number 12, boiling water is heated on a 2 kilowatt electric kettle. Okay, we've got that much water. That is the latent heat of vaporization. They want to know how long will this take? Well, Q equals ml. This is in your data booklet. And of course, the amount of heat energy we're going to put in is equal to the power times time, because power is equal to energy over time. In this case, the energy is heat, so Q. Do not confuse Q with charge in this context. So then to solve for E, or the energy, which is, again, our heat, Q, we just multiply the T up. So P times T equals ml. We want to solve for T, so divide the P over. M times L divided by P. The mass is 0.4. The latent heat of vaporization is 2 million joules per kilogram. And then the power is 2,000. Well, the 2's cancel out there, and this 1,000, I could have written 2 times 10 to the 3, right? And then that 2 would cancel out with that 2. This 3 would cancel out with that 6 to bring that 6 down to a 3, right? Because these are each just how many zeros. So I cancel out 3 of the zeros down here with 3 of the zeros up there. 0.4 times 10 to the 3. 0.4 times 1,000. 0.4 thousand. That's 400. Okay, gas storage tank, we've got constant volume. We've got N molecules at some temperature T. The initial pressure is 20 megapascals. And then we remove a quarter of the molecules. And we increase the pressure to 2T. What's going to be the pressure of the gas? Increase the temperature to 2T. I think I said increase the pressure to 2T. So we just use Pivner. Assume it's an ideal gas. PV equals nRT. We're curious about what happens with the pressure, so I divide the V over to isolate the T. The P. Now, the volume doesn't change and R doesn't change. What changes is N, the number of moles we have, and T, the temperature. So if we remove 1/4 of our particles, that means we have 3/4 remaining. And I just did 3/4 because we'll have 3/4 times N. R, I don't do anything with R. T is doubled. So I just do 2 for T. So 3/4 times 2 is 6/4, which is 1.5. Now that means our pressure is going to increase by a factor of 1.5 when we have 3/4 of the particles at double the temperature. Now this is just 3/4 and 2 because it's just n to the first power in t. If it was n divided by t, if the t was down here, it'd be 3/4 divided by 2. If it was n and t squared, it would be 3/4 times 2 squared, or 3/4 times 4. But they're each linear terms. And so then I just do a 1.5 times more pressure than 20. It's going to be 1.5 times 20. And then I get 30. So 30 megapascals. A particle performs simple harmonic motion. What is the phase difference between the displacement and the acceleration of the particle? So here I drew these 3 graphs for your benefit. So position versus time, velocity versus time, and acceleration versus time. For something in simple harmonic motion, I start off with a cosine. You could have started off with a sine, but I like to start off with cosine. So I did a cosine, and then to go from position to velocity, you look at the slope, right? Slope starts off at 0, goes negative, starts off at 0, goes negative, and that's maximum slope, so that's maximum velocity, negative slope, negative velocity. This has 0 slope, so we get to there, 0 velocity, and so on. So this is a positive cosine, this is a negative sine. And then to go from velocity to acceleration, we do the same thing. We look at slope of velocity to get to our acceleration, maximum negative slope on our velocity graph at the beginning, so maximum negative acceleration. 0 slope there, so 0 acceleration there. Maximum positive slope there, so maximum positive acceleration there. Looks like we get a negative cosine. Hey, a positive cosine and negative cosine are 180 degrees out of phase, or pi, because they're doing this in radians. Now, you could also do this or in a different way. You could say, well, if I've got an object oscillating back and forth from there to there at negative a, and it's going to go all the way to there and all the way to there. Well, when it's over here, its position is maximum positive, right? But its acceleration is going to be that way, maximum negative. So they must be 180 degrees out of phase because they're just always going the opposite directions. Which graph shows variation with time t for kinetic energy of an object undergoing simple harmonic motion? Well, kinetic energy is never negative, so that immediately eliminates B and A. And now we're between C and D. So, well, in one period, we go from, let's say we start here, and then there's our equilibrium, we end up there, so we go there and back again. So here we've got 0 kinetic energy, okay, at the very beginning. There we have maximum kinetic energy. That's only at 1/4 of a period, though. This looks like we have maximum kinetic energy at half of a period. No, 1/4 of a period. That's what that looks like. And then to there, at half of a period, we got 0 kinetic energy again because we've come to a stop. This was our equilibrium position where we have maximum kinetic energy. This is our maximum amplitude on the other side. Where 0 kinetic energy there. Ooh, that's not a whole period. That's only half a period. And then we come back, maximize kinetic energy as we go through the equilibrium position, and then we lose that kinetic energy in our spring or whatever is supplying the force as we get back to where we started at one period. So it has to be D. Number 16. What are the changes in speed, frequency, and wavelength for light as it travels from a material of low refractive index to high refractive index? Well, high refractive index means we're decreasing the speed of light, or the speed of the wave. So the speed must decrease. So that eliminates C only. The frequency does not change when you go from one index of refraction to the next, whether you're talking about sound or light or whatever. So frequency is unchanged, so that eliminates A. Now we're between B and D. And then the wavelength, well, if we decrease the speed and frequency is unchanged, we must be decreasing the wavelength because speed is equal to wavelength times frequency. So we must have decreased the wavelength. And that is how the effect occurs. That's how the refractive effect occurs. Which of these waves cannot be polarized? Well, so what kind of waves can't be polarized? Longitudinal. What kind of wave is longitudinal? Sound, ultrasound. Microwaves, ultraviolet, and X-rays, those are all electromagnetic. Electromagnetic waves are transverse waves made up of alternating electric and magnetic fields perpendicular to each other. So those can certainly be, electromagnetic waves can certainly be polarized. Sound waves cannot. A string fixed at both ends vibrates in the first harmonic. Okay, so first harmonic, which means the length of the string is equal to half of a wavelength because we have one bump. We know the speed of sound in the string. We know the frequency. What's the length of the string? Okay, well, velocity equals wavelength times frequency. We know frequency, we know velocity. We want the length of the string, and the length of the string is half of a wavelength. So let's find the wavelength. Wavelength is velocity divided by frequency. The frequency they gave us is, the velocity they gave us is 480. The frequency is 400. Now, you might think that's a bit much to do without a calculator, but that's not that bad, because 400 divided by 400 is 1, and then another 80. Well, what's a tenth of 400? It's 40. And this is therefore 2/10 of 400. So it's 1.2. Or you can do long division, I suppose, but I think that's the easier way to do it. And then, so the wavelength is 1.2. Take 1.2 divided by 2, because we want the length of the string, not the wavelength. That's 0.6 meters. B. Number 19. In science, models are extensively used to study real-life situations. So you have a situation where there's a drowning person in water. You can run on the beach faster than you can swim, probably. So how can you run? You don't want to take a straight line to them, because then you are going to be going at a slow speed too long through the water. You want to increase your length of time on the beach where you can run faster, so that you can shorten the distance where you go slower speed. And what phenomenon can we use to model this? By the way, Mr. Parks used to do this problem in his calculus class. I don't know if anyone still does this in math class. But the problem that we have done in this class that you can use to kind of model this is refraction. This is just like this person running is like a wave that's going into from one medium with a low refractive index to another one with a high refractive index. Faster here, slower there. So same exact thing. It's just like refraction. Number 20, two charges plus Q and minus Q are placed as shown. What's the magnitude of the electric field strength in descending order? So just remember that for a positive charge, electric field goes away. For a negative charge, electric field comes toward. So at point Z, we got our two charges here. Point Z, we're going to have our electric field in the positive one going that way, going away from Z, and from our negative one going toward. Did I say away from Z? I meant away from the charge, going toward that negative charge. So they're going to add up. So that one's going to be the strongest one. And the others, the two electric fields, are going to go opposite directions. So that's going to mitigate them. So Z has to be the strongest. A and D are gone. Now it's between X and Y. So Y is going to have a fairly strong electric field from plus Q. In fact, the same strength as Z had. But then Q, negative Q, is going to reduce that. However, not by as much as they increase this one, because it's farther away, almost twice as far away. So this one will be mitigated by that. And now this one, well, we're going to have a smaller, in fact, 1/4 of the strength of the magnetic field here at X from positive Q. And then from negative Q, a very small electric field, a 1/4 of this one. Did I say 1/2 of this one? I hope not for this one. I hope I didn't say 1/2. I hope I said almost twice as far. But this one actually is twice as far as Z from charge negative Q. So this will also mitigate that one. Now it's a question of which one of these. Well, the decrease in the strength of the electric field from the positive charge from here to here is greater than the decrease in strength from the negative charge. Therefore, this decreased more. This one decreased more than this one did, going from here to here. So this one is going to have the stronger electric field than this one overall. So it's going to be C. 21. Okay, we've got two cells, voltaic cells, each with an EMF of 9 volts, internal resistance of 3. They're connected in series, and then a 12 ohm resistor is connected in series with them. What's the current through the resistor? Well, everything in this has the same current because they're all in series. So current equals voltage divided by resistance for the entire circuit. The total EMF is 18 because we did two that have 9 and we put them in series. divided by the total resistance is the sum of the internal resistances and the external resistance of the 12 ohm resistor. So 18 divided by 3 plus 3 plus 12. 3 plus 3 plus 12 is 18. 18 divided by 18 is 1 amp. 22. Charge flows through a liquid. The charge flow is made up of positive and negative ions. Normally, charge flow in a conductor, a metal conductor that we've studied in our electricity and magnetism unit, is just the negative charge. It's just electrons move around, not protons. But here, we've got both positive and negative ions moving around in this liquid. In 1 second, we've got a flow of 10 coulombs of negative, 0.10 coulombs, 0.1 coulombs of negative ions in one direction and 0.1 coulombs of positive ions in the other direction. Now, the thing we've talked about with current is that conventional current is a direction of positive charge flow. However, electrons are actually the carrier of current in wires. These two are the same. So a positive charge going that way is the same as a negative charge going that way. So because we have 0.1 coulombs per second going that way, and then negative 0.1 coulombs per second going that way, well, that's just like 0.2 coulombs going that way, or negative 0.2 coulombs going that way. So it's 0.2 amps. That's an interesting question. It's a good one. Okay, now we have a beam of negative ions are going between these two poles of a magnet. And what's the direction in which the ions will be deflected? Well, the force on a moving charge through a magnetic field is equal to QVB sine theta. The sine is unnecessary here because that's the angle between the velocity, which is the current essentially, and the magnetic field is 90 degrees, right? So we have that and that. So that's 90 degrees. So we don't need this. Sine of 90 is 1. Now, electric fields go from positive to negative. So it's going to go that way. And you could do this one of two ways. You could do the right-hand rule for positive current, and then you get the force going whichever direction, then you flip it. Or I say, well, the beam of negative ions is going that way. That's like a current going that way. So that's like my velocity for my current going that way. Or you can say, well, they're negative, so that Q is negative. So it's just going to flip the sign either way. So I'm going to put my Q that way. I'm going to curl my fingers in the direction of B, and then my thumb points in the direction of the force, which is out of the page. A, out of the page. Number 24. This question seems strange to me. It seems way too easy. You have a motorcycle taking a turn on a banked curve. What combination of changes to the banking angle and the coefficient of friction could allow the motorcycle to take the turn at a higher speed? Well, a bigger coefficient of friction means more available friction. More available friction means more available centripetal force. More available centripetal force means you can take a turn at a higher speed. So it certainly increase your friction. So B and D are gone. And then the banking angle, a high banking angle also increases the speed at which you can take a turn, as we discussed briefly. Banking angles aren't really heavily covered in this class, so we only cover them very briefly. But a banked curve allows you to turn faster because you also get some component of the normal force that is going to be acting as a centripetal force because it's toward the center of the turn. So also increase the banking angle because then you increase a part of the normal force that is acting as centripetal force. That one seems strange. Too easy. Okay, satellite X orbits a planet with orbital radius r. Satellite Y orbits the same planet with orbital radius 2r. They have the same mass. What's the ratio of their centripetal accelerations? Well, for something that's orbiting, its centripetal acceleration is equal to little g, the gravitational field strength or acceleration due to gravity at that distance from the center of the planet. Well, g is big M, M being the mass of the planet, the central mass, divided by r squared. So to do this ratio, I would do g big M over r x squared divided by g big M over r y squared. Well, g and the big M will cancel out. I'm going to get, this is a double denominator right here. So I'm going to get ry squared over rx squared. Well, ry is equal to 2rx, right? And rx is equal to r. So 2r over r squared, that's going to be 4r squared over r squared. Those cancel out, 4d. Right. Or you can, if you're good at understanding ratios or proportional reasoning, you can just realize, hey, well, this centripetal acceleration of y is going to have to be 1/4 as much because it's twice as far away and the distance is an inverse square. Just make sure you don't say 1/4 by accident, because you get that this one has centripetal acceleration 1/4 as much. It turns into a double denominator. 26. Which property of a nuclide does not change as a result of a beta decay? So a beta decay either turns a proton into a neutron or a neutron into a proton. In the case of a neutron to a proton, that's a beta plus decay, where it is emitting a electron and a positron, and an electron neutrino. In the case of a proton to a neutron, it's beta minus decay, we're emitting an electron and an anti-electron neutrino. But either way, you're just converting a proton to a neutron or a neutron to a proton. So the proton number and neutron number don't stay the same. The charge doesn't stay the same because this is charged. The protons are charged and neutrons are not charged. But the nucleon number does stay the same because these are both nucleons. So it's A. Rest mass of the helium isotope 3, or helium-3, is M, which expression gives a binding energy per nucleon. Well, immediately you can eliminate C and D because it's per nucleon. There are 3 nucleons, so you're going to have to take the total binding energy and divide it by 3. So C and D go away immediately. Now, to find the binding energy, what you do is you take the energy equivalent of the mass of each particle that this isotope is made of, and you subtract from that the energy associated with the rest mass of the overall particle, and that gets you the binding energy. And then per nucleon, divide by 3. So there are 2 protons, right? See, 2 protons. So that's 2 times the mass of the proton. Plus, well, there must be 1 neutron, right? Because the total mass number is 3. We have 3 nucleons. So 1 mass of a neutron. And then, oops, I meant to be pointing down here. And then we subtract the overall rest mass of the helium-3, which they just called M. Now, multiplying by C squared here, that's associated with converting these masses into energy equivalents. And so the answer is B. Which of the following atomic energy level transitions corresponds to photons of the shortest wavelength? So, well, short wavelength means high frequency because velocity is the same for any photons that leave this, right? Because all photons travel at the speed of light, c. C is equal to lambda times frequency. Keep in mind that in the data booklet, IB seems to use C, and probably in the test seems to use C for the wave speed. I use C just for the speed of light in a vacuum. So that's kind of annoying. Anyway, if this decreases, we want the shortest wavelength, so that means we want a higher frequency. Well, higher frequencies corresponds to a higher energy because energy equals h Planck's constant times frequency. So energy of a photon is based on its frequency. I guess you could say it's based on its wavelength too, because then energy would just be, what would it be? It would be hc over wavelength. You could do it like that as well, but that seems silly to me. So I would just go straight to this. And so we want the biggest drop in energy, which is C. Right. How much energy is lost corresponds to how long the arrow is there. Number 29, a beaker. This question I think is horribly written. When I first read this, I thought it was asking what is the rate of the initial rate of change of temperature after you remove it from the hot plate. That's what's clearly implied here, in my opinion. Please let me know if you agree. But that's not what it's asking about at all. In fact, this was completely irrelevant. You didn't learn how to do this in this class because it's not part of the curriculum. This would be a Newton's law of cooling problem where we'd have to know something about the cooling. We'd have a cooling constant that we need to deal with. But that's not what it's asking about. It's asking about this. We have a beaker of 1 kilogram of water, and these are the same situations, just that we're heating it up here and then we take it off the heat once it starts to boil. But this question is not asking about the change in temperature, the rate of change of temperature after you take it off the heat. I don't know what they were thinking when they organized this question. This is a horrible question. The physics behind this question that they meant to ask is very good, but the way they did is horrible. So a beaker containing 1 kilogram of water on a 400-watt hot plate with that specific heat capacity for water. So we say, okay, well, Q equals MCAT. This question is also in the wrong place. Right? Typically, they go from topic 1 to topic 8 here. This is a topic 3 question at the very end when we're supposed to be doing topic 7 or 8 questions. So Q equals MCAT. We know C. We know M. We don't know Q, but we do know that the energy put in is equal to power times time. Right? Because power is equal to energy or work over time, or heat over time. So to solve for the heat, we just multiply the time over. And now we want to know the rate of change. So what I do then is, well, the rate of change is the change in temperature in a certain amount of time. So I divided the time down there to get delta T over T, and then I got rid of this MC by multiplying it under the P. So I get the rate of change of temperature, change in temperature over change in time, is equal to power divided by M times C, which would be 400 divided by 1 times 4200, which is not exactly 0.1, but it's approximately 0.1. So the temperature will be increasing by 0.1 Kelvin per second. Right. Kelvin, units there's Kelvin, units there are seconds. Kelvin per second. Now, another way you can guess, I suppose, that this whole thing is irrelevant is that what will be the initial rate of change of temperature? They don't say magnitude. And all these are positive, which implies that the temperature should be increasing. So it can't be after the water starts to cool when you remove it from the hot plate. Although I guess, well, it's increased until it reaches a constant value. That must mean it's boiling. So when you take it off the hot plate, it won't immediately start to cool, I suppose, because the energy from the hot plate at that instant was going into... Now, yeah, this is a bad question. That should not have been there. Number 30. Most power stations rely on a turbine and a generator to produce electrical energy. Which power station works on a different principle? Solar. Right. Nuclear, you use the nuclear fuel to boil water, which runs a turbine, which runs a generator. Fossil fuel, you burn the fossil fuel to boil water, which turns to steam, which runs a turbine, which runs a generator. Wind, well, wind goes through the turbine blades, which runs a generator. Solar, voltaic, specifically solar voltaic, but also solar heating, I suppose, sometimes. Solar voltaic works on a completely different principle where photons come in with enough energy to knock electrons out of the material, and that's how they produce current or voltage to produce electrical energy. So that is B. All right, there you go. That is paper 1 of the May 2019 IB Physics SL exam, version 1.